Greetings of the day to all of you. Today we are going to start the third module of our course on flexible AC transmission systems. So we are going to start module 3. In module 3 we will be mainly discussing about various shunt and series compensators. Shunt compensators especially are SVC and STATCOM, and then there are different types of series compensators also. So in module 3 we will start our discussions on first type of shunt compensator, that is static wire compensator, SVC. So static wire compensator. Now, I have already given you the idea about a static wire compensator. It's basically a shunt compensator which exchanges the reactive power with the system bus or with the transmission line, and hence it results in various various advantages, like it increases the power transfer capability of an existing transmission network. It helps in quick damping of electromechanical oscillations or power oscillations. Okay, it provides the voltage support for voltage balance of a system, and so on. So these advantages we have already discussed. Now I have also discussed with you the schematic diagram of a static wire compensator. The main components of a static wire compensator are thyristor controlled reactor, TCR, and either a fixed capacitor bank or a switched capacitor bank. And if the capacitor bank is switched, then switching may be done either through mechanical switches or through electronic switches. If switching is done through mechanical switches, then we have mechanically switched capacitor. And if switching is done electronically, then we have thyristor switched capacitor, TSC. As far as TCR and TSC are concerned, which are very important components of an SVC, we have in details discussed about the configuration and operation of these, both of these components in the module 2. Okay, so various types of static wire compensators, which are also called SVCs. Various types are: number 1, mechanically switched capacitor, thyristor controlled reactor type, SVC. An SVC which uses TCR for reactive power absorption, and which uses a capacitor bank, but the capacitor bank is mechanically switched. That's why we have mechanically switched capacitor, MSC, TCR, SVC. Second type is where capacitor is fixed. So fixed capacitor dash TCR type, SVC. The capacitor bank is permanently fixed to the system, and it continuously generates the reactive power and keeps on injecting that reactive power into the system. So it is FC, TCR, SVC. And third and the most important type of SVC is TSC, TCR type, SVC. In TSC, TCR type SVC, the capacitor bank is electronically switched. Instead of using mechanically switched capacitor bank or fixed capacitor bank, we are using thyristor switched capacitor bank, TSC. So it is TSC, TCR type, SVC. So we have to discuss, so these are three main types of static wire compensator, SVC. MSC, TCR, SVC, that means mechanically switched capacitor, thyristor controlled reactor type, SVC. Then fixed capacitor, thyristor controlled reactor type, SVC, that's FC, TCR, SVC. And finally, thyristor switched capacitor, thyristor controlled reactor type, SVC, that is TSC, TCR, SVC. We will discuss them one by one. And in today's lecture, we will discuss the first type of SVC, that is mechanically switched capacitor. And SVC where capacitor bank is mechanically switched, I will write here mechanically switched capacitor dash thyristor controlled reactor, thyristor controlled reactor, that is MSC-TCR SVC. and SVC where the capacitor bank is mechanically switched, and along with capacitor bank we have a thyristor controlled reactor. So it is mechanically switched capacitor, thyristor controlled reactor, SVC, that is MSC, TCR, SVC. In certain applications, especially those involving only a few capacitor switchings in a day, where large number of switchings are not involved, only a few capacitor switchings are involved, this type of SVC, that is MSC, TCR type SVC, has been shown to offer acceptable performance at lower costs than a TSC, TCR, SVC. Because since number of, mechanically switched capacitor bank is cheaper than thyristor switched capacitor bank. Okay, MSC is cheaper than TSC. So therefore, in those applications where only a few number of switchings per day are involved, this MSC TCR type SVC offers lower costs than an equivalent TSC TCR type SVC. Okay. Now the configuration of this SVC is like this. This is our high voltage SVC bus, or high voltage compensator bus also we can say. Then we have a step down transformer like this. This creates medium voltage compensator bus, medium voltage SVC bus. And to this medium voltage SVC bus we are connecting mechanically switched capacitor banks like this. Maybe more than one capacitor banks connected in parallel. So these are mechanically switched capacitors, MSCs. Okay. And then we have thyristor controlled reactor, TCR. And this is the circuit diagram of TCR. This is TCR. And of course, in order to suppress the harmonics, especially lower order harmonics, we have to connect filter, harmonic filter. So this is our harmonic filter. So all these components are connected to a medium voltage bus. Okay. Now this is mechanically switched capacitors whose job is, whenever they are switched in, to generate the reactive power and inject the reactive power into the medium voltage bus, and then through this transformer inject that reactive power or leading wires into this high voltage SVC bus. The job of TCR is to absorb the excess reactive power, leading wires, which may be there flowing on the system. And the job of the harmonic filters or harmonic filter is to suppress certain harmonics. Another configuration may be like this. Again, this is our high voltage SVC bus. And then these are the mechanically switched capacitors which are directly connected to high voltage bus. These are mechanically switched capacitors, MSCs. And then the medium voltage bus is created like this. This is medium voltage bus, MV SVC bus. And to this medium voltage SVC bus we are connecting the remaining parts, like thyristor controlled reactor is connected like this. This is TCR, inductor reactor also has to be connected. This is TCR and harmonic filters. Okay, and then this is the harmonic filter. This is harmonic filter. The capacitor bank may be directly connected to high voltage bus, but as far as TCR and these filters are concerned, they have to be connected to medium voltage bus, because if you connect TCR to high voltage bus, then you need high voltage rating devices which may not be available in the market. And to avoid the use of large number of thyristors in series, we transform this high voltage bus to medium voltage bus and then connect the TCR's valves, and hence the TCR in this fashion. And instead of connecting the harmonic filters to high voltage bus, we have to connect harmonic filters to medium voltage bus, because when they are connected to medium voltage bus, the harmonic currents drawn by the TCR will be always flowing through the transformer primary and secondary windings. And to rid the transformer windings of these harmonic currents, it is advisable to connect the harmonic filters at the medium voltage bus, not at the high voltage bus. Okay, so these are two different configurations of MSC TCR type SVC. In this configuration, all the components are connected to medium voltage SVC bus, and in this configuration, TCR and harmonic filters, they are connected to medium voltage bus, but MSCs are connected to high voltage bus. Fine. Now, there are certain advantages offered by this MSC TCR SVC bus over TSC TCR SVC bus. So let us first of all identify the advantages offered. Okay, advantages are: number one, lower capital cost. Lower capital cost on account of the first advantage is lower capital cost on account of elimination of costly thyristor valves. In capacitor banks. In the capacitor banks, let me draw the diagram again. I should not have erased it. High voltage SVC bus, then we have a step down transformer like this, and we have medium voltage SVC bus, and these are mechanically switched capacitors like this. These are MSCs, and we have thyristor controlled reactor TCR, let me tell you, this is basically, it's not a single TCR, it's a segmented TCR. One TCR and many TSRs are connected in parallel. Because of the non-availability of space, I am showing just one TCR, but actually it is segmented TCR. So let me write TCR here, and then we have harmonic filter like this. This is harmonic filter. Now, whenever there is large reactive power requirement by the load has a poor lagging power factor, then the reactive power is generated by these capacitor banks. They are switched in, and that reactive power compensation is done by the capacitor bank. And if the reactive power leading wires injected, or reactive power injected by these mechanically switched capacitor banks is more than what is required by the load, then the remaining or excess leading wires or excess reactive power is absorbed by the TCR by delay angle or firing angle control. And then these two balance the reactive power supply on the bus, and hence they maintain the bus voltage nearly constant. They provide the bus voltage support, improve the voltage stability of the system, improve the transient stability of the system, quickly damp the electromechanical oscillations, and also increase the power handling capability or power transfer capability of the existing transmission line. Okay, so this is how the SVC works. Okay, so the mechanically switched capacitors and segmented TCR, they work in tandem. They work together to do the reactive power compensation. Okay, now since in mechanically switched capacitors we are not using any thyristor valves, whereas in thyristor switched capacitor, which we have studied in module 2 last lecture, we are using the anti-parallel connected pair of valves or thyristors. I have shown you in the last lecture. We don't use any these thyristor valves. Thyristor valves are very costly. Those thyristor valves are replaced by mechanical switches, and mechanical switches are fairly cheap. So therefore, since the thyristor valves in the capacitor banks are eliminated on account of elimination of costly thyristor valves, the cost of these capacitor banks is decreased, so overall cost of MSC TCR SVC is low. This is first advantage. Second advantage is reduced losses, reduced power losses, and power losses are in the range. Power losses are in the range of 0.02 to 0.05%. So power loss in this type of SVC, MSC TCR SVC, is very, very low, 0.02 to 0.05% of total power rating of SVC. which is lowest of all SVCs. Why the power loss is reduced? Because in these mechanically switched capacitors, the thyristor valves are reduced, and the conduction and switching losses of those thyristor valves are, they don't exist. So since those losses are eliminated, so overall losses of the complete SVC are reduced. They are in a very low range, 0.02 to 0.05%. So these are the advantages offered by MSC, TCR, SVC. However, this type of SVC suffers from some serious drawbacks. Let us try to identify the drawbacks of this type of SVC. Main drawbacks. First drawback is that this type of SVC gives slow response. It is slow in response, or it has a sluggish response. Okay, I will write here a mechanical switch takes 2 cycles to close and 8 cycles to open. 8 cycles to open as against 1/2 cycle to close, that's half cycle to close, and 2 cycles to open by thyristor switched capacitor or by thyristor valve, which is used in thyristor switched capacitor. A thyristor valve closes very quickly in half cycle and opens in just 2 cycles, whereas a mechanical switch, which is used in this type of SVC, it takes 2 cycles to close and about 8 cycles to open. So therefore, whenever you need a quick response, quick closing and quick opening, that is not possible with MSC, TCR, SVC. So therefore, MSC, TCR, SVC gives slow response. Therefore, it finds its applications where a fast response is not mandatory, where the fast response is not required. This is one main drawback. Another drawback is trapped charge in capacitor banks after de-energization. De-energization. See, whenever these switches are opened, there is certain voltage or certain charge which will be retained by these capacitors, and there will be certain capacitor voltage. Okay, capacitor will always have, these capacitor banks will always have certain voltage because of trapped charge. When they are opened, when the switches are opened, when the capacitor banks are de-energized, they have certain trapped charge. Okay, now in order to remove that trapped charge, resistors which are inbuilt within the capacitor banks, they are generally, if these parallel resistors, discharging resistors are connected, then the capacitor banks, when they are opened, they discharge through these resistors, but the discharge time is very, very high. So discharge time through parallel connected resistors, we can call them discharge resistors, is about 5 minutes. So they take about 5 minutes to discharge completely and remove all the trapped energy. But during this period, if operation of TSC is required, then before the capacitor banks have discharged completely, you may have to close the capacitor banks, and if capacitor banks are closed with certain trapped energy, still some trapped energy in them, it results in transient switching, high current switching and transient switching that may damage the capacitor banks. Okay, to avoid that, we want fast discharge of these capacitor banks when they are de-energized. And how can we discharge them fast? If parallel transformers like PTs, potential transformers, small PTs are connected, instead of connecting these resistors, small parallel transformers like PTs are connected across the capacitor banks, and the capacitor banks then very quickly discharge. Instead of taking 5 minutes to discharge, they take only 0.15 second to discharge. That results in quick discharge. But again, the PTs are not free of cost. They involve certain cost. So you have to invest on PTs and connect them across the capacitor banks for quick discharge. Okay, so this is second drawback. Third drawback is that these mechanically switched capacitors, they use mechanical switches, and mechanical switches have got finite lifetime. Finite lifetime, generally 2000 to 5000 operations, switching operations. The life of these mechanical switches is about 2000 to 5000 operations. After 5000 operations, you have to replace these mechanical switches, because because of the mechanical switching, turning on and turning off, there is always a wear and tear, and they have got, these mechanical switches have got finite lifetime. And how much lifetime? In terms of switching operations, about 2000 switching operations to 5000 switching operations only. Okay. On the other hand, these thyristor valves, which are used as switches in thyristor switched capacitors, they have ideally they have infinite lifetime. So therefore, in TSC, TCR, SVC, we are using thyristor valves as switches. They have infinite lifetime. And on the other hand, in MSC, TCR, SVC, we are using mechanical switches. And mechanical switches have got finite lifetime. And this finite lifetime is about, it involves 2000 to 5000 operations. Okay, so generally that's why I said in the beginning itself that these MSC, TCR, SVC is suitable only in those applications where only a few operations are involved in a day. For example, they are used in those applications where 2 to 4 switching operations are required per day. 2 to 4 switching operations only per day are required. Okay, generally these capacitors, MSCs, mechanically switched capacitors, are closed during peak load hours, because during peak load hours most of the industrial load is connected and they demand the reactive power, and that reactive power is generated and injected into the transmission line by these mechanically switched capacitors. And during light load hours, they are opened. During light load hours, you don't need any reactive power because most of the industrial load is switched off. So therefore you don't need a reactive power injection. So they are opened during light load operations, light load hours. So where only 2 to 4 switching operations per day are required, we prefer this MSC, TCR type SVC because number of switching operations is very limited, just 2 to 4 switching operations per day. Another very important point that you must understand is that is in fact another drawback as far as this TCR is concerned. TCR is in this MSC, TCR, SVC, TCR is designed for smaller inductance with some overload capacity to transiently balance the capacitive reactive power, the capacitive reactive power. I mean, whatever is the reactive power, capacitive reactive power injected by these capacitor banks, a part of that may have to be absorbed by the TCR. So TCR is operated at a certain delay angle and it balances the capacitive reactive power output of this capacitor bank. But this TCR is in MSC TCR type SVC, it is designed for low value of inductance, but not for high value of inductance. Okay, and that means when a TCR has low value of inductance, it will be rich harmonic currents will be drawn by this TCR. Rich harmonic currents. The harmonic content in the currents will be very high as compared to a TCR with high value of inductance. So harmonic content of current is high. So you need your filtering requirements may then increase. So this is another drawback of MSc TCR SVC. Since MSc TCR SVC has a TCR with low value of inductance, and the TCR draws the harmonic the currents which are very rich in harmonic. The harmonic content in the line currents is very large, and your filtering requirements increase. Okay, so therefore, understanding the advantages and drawbacks of the MSc TCR SVC, now we can identify the area of application of MSc TCR SVC. Area or areas of application. Where do they find their applications? Obviously, they cannot be used in those applications where frequent disturbances occur. Because where frequent disturbances occur, and we use this MSc TCR SVC, for frequent disturbances you need quick response, quick operation, switching operation. You may have to very quickly switch on the SVC and quickly switch it off, okay, for one disturbance, and immediately second disturbance may come after a few cycles. You may have to again switch it on, and so on. So in those applications where quick disturbances are there, we can say that an MSc TCR SVC may not be very suitable for voltage control applications in a system experiencing frequent disturbances. Shall I write it? So let me write it. An MSc TCR type SVC is not suitable for applications involving frequent disturbances. Is not suitable for applications involving frequent disturbances. Why? Because of its slow response. And because of slow response and limited lifetime of switches. Limited lifetime of switches. These are the two reasons because of which an MSc TCR SVC is not suitable for those applications where there are frequent disturbances. It's not suitable. Okay. So generally it has been seen, a study reveals that MSc TCR SVC provides performance comparable to TSC TCR SVC in damping power swings. So therefore applications are MSc, I will write here, MSc TCR SVC provides comparable performance in damping. Comparable performance means performance compared to TSC TCR SVC in damping power swings between two areas. So if you have two areas and those two areas are suffering power swings, you may use MSc TCR SVC because it does not involve frequent disturbances and it can very easily damp those power swings between the two areas, and its performance will be comparable as good as that of TSC TCR SVC, but at a lower cost. MSc TCR SVC provides comparable performance at lower cost in this type of application, in damping power swings between two areas. That is one application. Another application is that this MSc TCR SVC is used for alleviating severe voltage sags in applications for alleviating severe voltage sags from system faults. So there may be some short circuit, some fault that will result in severe voltage sag, And where there is severe voltage sag, I have already told you a shunt compensator injects the reactive power into the bus and it provides the voltage support and it prevents the severe voltage sag by providing the voltage support. So this is another area of application of MSc TCR SVC. So therefore MSc TCR SVC is not suitable for applications involving frequent disturbances. So therefore its areas of applications are like this. Number one, it provides a comparable performance at a lower cost in damping power swings between two areas because it does not involve fast switching operation. And it is also used in applications for alleviating severe voltage drops from system faults because these faults occur once in a while, they don't occur frequently. So since frequent switching is not required, so MSc TCR type SVC is suitable for this application also at a reduced installed cost or at a reduced cost as compared to TSC TCR SVC. So therefore for those applications where frequent switching operation is not required, like for damping power swings between two areas and for alleviating severe voltage sags from system faults, MSc TCR SVC finds its application at a reduced installation cost or at a reduced cost. And finally, let me tell you that since capacitors are very sensitive over voltages and over currents, appropriate protection strategies need to be employed. So you have to provide over voltage protection of capacitor banks and also over current protection of capacitor banks. So that's all about the first type of SVC, that's MSc TCR SVC. We have seen, we have drawn the schematic diagram of MSc TCR SVC. We have seen the capacitor banks are mechanically switched, not electronically switched, and we have identified some drawbacks and some advantages. Advantages are, these advantages are lower capital cost because SCRs are not involved there in the capacitor banks. Due to the elimination of SCR valves, the capital cost of MSc TCR SVC is low, and it also results in reduced losses in the range of only 0.02 to 0.05%. But it has certain drawbacks, like first drawback is slow response, second drawback is trapped charge left after de-energization, which you have to release, or you have to remove that trapped charge. And the MSc TCR SVC should be switched in only when all the trapped charge has been removed. And another drawback is finite lifetime. The mechanical switches have finite lifetime, about 2000 to 5000 operations only, as compared to the infinite lifetime of thyristor switches. And another drawback is large harmonic content in the line currents because of lower value of inductance in TCR, for which filtering requirements are higher than those in TSC TCR SVC. And therefore we have identified the areas of applications. We have first of all seen that it cannot be used, this MSc TCR SVC cannot be used in those applications involving frequent disturbances due to slow response and due to finite switch lifetime. Therefore its areas of applications are like where between the two areas there are power swings. For damping those power swings, MSc TCR SVC is a very good choice. It gives as good performance as other type of SVCs like TSC TCR SVC, but at a reduced cost. And second application we have identified for alleviating severe voltage sags because of system faults, again at a lower installed cost as compared to TSC TCR SVC. And finally, for over voltage and over current protection strategies have to be used for over voltage and over current protection of capacitor banks. So that is all about the first type of static wire compensator, the first type of SVC, that is MSc TCR SVC. I advise all of you to go through this lecture, study this, and in case of any queries, you are free to ask or put your queries on the group or on the YouTube channel. I'll be pleased to reply your queries. I wish all the best to all of you. Thank you.